So once again, we calculated the finishes. We have got the live load. We have got W, which is 1.4 plus 1.6 live load. And then we have got our self weight, which is 24 into D. But D is not yet available. So we need to go and calculate it. After that, we'll be only able to be calculating our W. And then based on W, we'll go and calculate our moment. Now for moment, it depends on one way or two way. So we have checked whether it's one way or two way. We have long direction, which is 7. We have short direction, which is 3. So 7 divided by 3 is more than 2. More than 2 means one-way slab. A one-way slab, if it's not mentioned that it's connected to something else, and it should be taken as simply supported case, where our moment equation is WL square over 8. Okay. Now, if it says for you that what you call that there is connection, if it says for you that there is any connection, then you should use WL square over 8. Okay. So WL square over 8, where W is going to be calculated from here. For one-way slab, Sulaiman, you should have it from you have studied it in the previous courses, but you can see it here as well. This is for a two-way slab, but simple. For your one-way slab, if it's continuous, I have already uploaded for you in the Teams. I have uploaded for you the codes. So we go for the code, which is BS8110. Okay. Okay. Where this is for beams. You have studied this table, right? First interior, outer support. Okay, so this is for a beam. And this is for your slab. So you don't remember, any of you don't remember how you have done in what you call in your RC design, in your design of structures 1. So in this way I need to repeat everything that we have studied. Okay. So outer support, near middle end or near middle of end span, and then we have outer support, end span, first interior, middle interior, and then interior. If anybody does not know how they don't know how to do it, let me know so I'll explain it now better. If anyone is suspecting that he does not remember, let me know now better, then it's coming for you in the exam. You have seen I have opened it, right? Sulaiman, have you seen it? Asma, I have just opened it for you. Okay. It is this one. Ultimate bending moment and shear forces in one-way spanning slabs. Okay.
Mister, from here we can find the coefficient.
These are the coefficients. The values are the coefficients.
Okay.
Okay. Are we fine? Okay. Now I'll try just to explain. What do we have? We have two types of spans. We have something called end span, and we have something called interior span, and then we have for support. We have end support or outer support, and then we have first interior, and then we have interior support. Okay. Now, if you see, we have this situation. We have another situation. We have this situation. And then we have this situation. Okay. Now, first we'll try to check for the spans. First, we'll try to check for the spans. Okay. So end span, I'll try first to go for end span. If we see, this is my end span, this is my end span. I told you, if we go and see, this is whatever we call it as span, if you remember, and this is whatever we call it as support or edge. Do you remember? Okay. So span, 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 span. These are end spans. The outer ones, the outside ones, we call them outer spans. Okay. Or end spans. So end span, end span. For the interior, whatever is not the end, whatever is not in the end, then we call it as interior. So interior, 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 and then interior. Now, when we go to end, what you call, when we go to the support, we have end, first interior, and then interior. The outer ones are called to be end or outer supports. They are outside. Okay, it's like you are coming from outside. Whatever columns you will face or whatever beams you will face, these are representing your outer support. Whatever comes after the outer support, we call them as first interior. So outer, first interior, whatever comes else is going to be interior. Outer, outer, first interior, and then interior. Outer, outer, first interior, outer, outer, first interior, and then first interior. Now, do you remember when we talked about a continuous and a simple support? Do you remember this thing? We said we have simple and continuous. Do you remember? Okay. Now, if you go to your table, if you go to your table, you can see that we have two types here. We have one is outer, which is here, outer for simple, and then outer for continuous. And then we have end span for simple, and then we have end span for continuous. So if we return back to our presentation and see, now this one is considered to be outer, but the category is continuous. This one is considered outer, but the category is simple. Do you remember? For example, if I go and create another slide, and I want to go and calculate, for two scenarios. Okay. Now if we go and try to draw the bending moment starts from 0, it goes up, 0 up, 0 up, and then like this. For the continuous, we said it goes from up one side and then this way. Do you remember the drawings? Okay. So if we go and see, first we'll try to finish the support. It says for you simple. We have simple support. The bending moment is 0 and the end span is 0.086. So 0 and 0.086. So returning back here. So this is going to be your 0. This is your 0. This is the span. So this value of this coefficient is 0.086. And this one is 0.086. Okay. Are we fine? We are fine with that? Okay. Returning back to our remaining things. So we have finished from the simple. Of course, it cannot be simple and continuous at the same time. So remaining for us is going to be first interior, middle interior, and then interior support. Okay, so we have 0.086, then we have 0.063. So we'll return back. So for first interior, 0.086 will come here. We said that this is going to be this is the outer. These are first interior. You remember if you are coming from outside, first interior. Okay, so this value is minus 0.086. Now this value is minus 0.086. Minus represent negative bending moment. Positive represent positive or down bending moment. Okay. And then we have 0.063 and minus 0.086. 0.063. So this is the span. So if we see here, this one now is 0.063. This is 0.063, and this is minus 0.063. Are we clear? Are we clear? Any further question about how to use it? Correct. Now for the continuous, you can see that these are changing, only the outer ones. So the outer support and the end of middle, or the whatever we call it as end span. So we'll return back here. So only what you can see, this one is the same as this one. Okay, this is the same. This is the same. The only thing changing for you are going to be your supports and end span. Support and end span. So we have it as 0.4 minus 0.04 and 0.075. So now, because you can see that there is a moment, of course, 0.04, and this is 0.04, and this one and this one is 0.075. This one 0.075. Okay. Where this one and this one are exactly as it goes here, because the change is happening only in the last support, and the last support will affect the end span only. Are we clear? Very good. Returning back to our question, do you have anything before going to the question? I have given you these exercises, assuming that you should be fine with the design of structures. Do you have any questions before continuing solving this question? Okay. So now we need to calculate our D capital. Okay. We need to calculate our D capital. To calculate our D capital, we need first to get our D small. Okay. And D small can be calculated from the equation of span divided by modification factor multiplied by ratio. Do you remember this equation? If you don't remember it, tell me, so I'll tell you from where did you get it. If you remember it, then it's fine. You shouldn't memorize. Now you don't remember whatever you have taken in design 1 because you were remembering the equations. You were memorizing the equations rather than remembering. Okay. So returning back, we said D is equal to span divided by modification factor to ratio. Now what does this mean? What does this mean? Actually, this started coming from an equation which is span by effective depth should be limited to a certain ratio to ensure, okay, to ensure that this structure is economic. Do you remember when I told you? Do you remember when I said the different types of slabs? And I said like 6, 7 meters, 8, 5 meters. Do you remember these values? These values are derived from these equations only. So based on a certain span and that certain ratio which they found to be optimum, you should be having this amount of depth. Okay. Now, if you remember, we have cantilever for 7, we have simply supported for 20, and then we have continuous for 26. Okay. It means that if I have a span of 6,000, if I have a span of 6,000, and I need to maintain a ratio of, let's say, simply supported, which is 20. Okay, or let us not do that. Try to release this person. It's not possible. Okay, so let's say that this was 3,000 rather than 6,000. 3,000 because we are designing for the short span, if you remember. So 3,000. Okay. Now 3,000 divided by d should equal to 20. It means that d is equal to 3,000 divided by 3,000 divided by 20. Okay, and if we try to go and calculate 3,000 divided by 20, it will give you 150. But the code says for you, now if you remember, this 3,000 is representing your span, 3,000. D small is representing D small. Ratio is 20 is representing the ratio. Now the BS code says for you, if the member is designed mainly for deflection, one of the major failures is deflection, then it needs to have a modification factor to control the deflection. Okay, and I'll show you in the code where these are coming from. Okay. Now slab is mainly failing in deflection. Slab will not fail regularly in bending or in shear. Okay, once again, slab will not fail in bending and shear regularly. It will fail in deflection. And the reason, when we have the loading, you will see that the loading for the slab is distributed among or distributed along the entire area. Okay, so we don't have very big load in a certain place. The load is distributed. Okay, the load is distributed compared to the beams and the columns. Okay, so it means since the loading is small, it means that your bending moment and your shear forces are small. If you remember, shear force was a function of coefficient N or W multiplied by L. Moment is a function of coefficient W multiplied by L square. Do you remember? If your loading are small, it means that your shear and your bending moment are small. Okay. So once again, when it comes to slab normally does not fail in bending or shear. whatever you have taken in design one, you have not seen a slab which is a doubly reinforced slab, but you have seen a beam which is doubly reinforced. You should have asked yourself why the beam we have got doubly, but we didn't get it in the slab. Why do we have links, shear reinforcement in the beams? We don't have them in slabs. Okay. So you should ask yourself these questions, otherwise you keep on memorizing rather than understanding. Once again, the fact that the loading is distributed along a big area, it means for a certain position, the loading is going to be small, which will take moment and shear to be small. Now, when we talk about deflection, now, since it's a large area, of course, it will deflect more. Example of A4 paper and A0 paper. If you handle it from the sides, A0, you will see that it will deflect from the middle. A4, you will see that it will deflect from the middle as well, but a very small value compared to A0, which is having a greater deflection. Are we clear? So once again, slab normally fails in deflection, but we are checking it for bending and shear. Beam is normally failing in bending and shear, but we are checking it as well for deflection. Are we clear? Okay. So once again, for the beam, we are not going to use the modification factor. We are not going to use the modification factor because you don't need to control it for deflection. Okay. Now let us go to the code. Let us go to the code and see from where we have got all of these things. I think I can find you the extracts. Try to search for the extracts if I could find them. It would be easier. Let me check it in your e-learning. Okay. No, 0.086 is different from 1/8. 1/8 is having 0.125. 0.086 is different. Now, can you see the extract? I think you will be getting this one for your what you call it. It's a little bit simpler than the bigger code. Okay, I'll try to upload it for you. Now everything has been mentioned here. Like for example, if you want to get the shear, deflection, almost everything is mentioned. Let us try to see the deflection. So deflection requirement. You mean for the one-way slab? You mean for the one-way slab? Or you mean for shear? Amira, one-way slab or shear? The table of one-way slab, you mean? Can anybody answer why this is only WFL, not what you call? Why this is FL? We said if you remember, moment is a function of beta W into L square. I have given you this general equation. Now, in this particular code, it says for you only, for example, 0.086 FL. Why not L square? Anybody knows the answer? No, of course. Okay. Now the answer is as Asma said. Okay. The answer is as Asma said. F is actually a multiplication of W into L. So this is taken as W multiplied by L multiplied by L. So always this general formula is correct. To keep it simple, normally we have W and then we have F. Let's say let's start from the opposite. We have F, we have W, and then we have N. Normally this is in kilonewton. This is in kilonewton per meter, and this is normally in kilonewton per meter square. Although they mean the same things. Okay, they mean the same thing. So here when I say F, it's in kilonewton actually. Okay. So kilonewton then meter. So kilonewton meter and then multiplied by meter. Okay. Is it clear now, Amira? Okay. Now we'll go for the code. This is extra. It says for you here, this is what we have said. We have 7. Normally I give the student this one for their exams. So we have 7, 20, and then 26. Now if you see the definition, it says for you basic span by effective depth ratio. Okay, so basic span divided by effective depth ratio. Okay, so whatever we have said earlier, and then it says for you this is related to deflection. So the span by effective depth ratio should therefore be modified according to the ultimate design moment and the service stresses. So now if you can see the table that you have used for the calculation of modification factor, you remember this equation, right? This table, you remember? Okay. So a lot of you will be asking from where we used to get 1.3 and 1.4. 1.3 and 1.4 actually are from here, from this particular line. So we are using FY 460. Okay. For 460, and normally the range of M to BD square for slabs is between 0.7 to 1. Normally, the regular range. So that's why we are assuming that it is between 1.3 to 1.4. Is it clear? Are we fine? Okay. So now we have a modification factor that we should use. Okay, we have a modification factor we should use. Now it says for us, okay, it says for us that we have span by effective depth. Okay, span by effective depth. Okay, equal to a certain ratio. Do you agree that span divided by effective depth should equal to a certain ratio? Okay. Now, according to that statement, that paragraph we have read, it says that the ratio needs to be multiplied. Okay, it says that the ratio needs to be multiplied by a modification factor. So I just multiplied it by ml. I multiplied the ratio by ml. So now if we rearrange the equation, we bring effective depth here, then I can say effective depth is equal to span divided by ratio into modification factor. Are we clear? Is it clear now? From where did you get this equation? Any question about it? So returning back here, we return back to the same equation. So now our span is 3000 because we are designing for the short. So 3000. Modification factor can be assumed as 1.4. Ratio, since it's simply supported, the ratio is 20. Remember, we opened this one saying cantilever 7, simply supported 20, and a continuous is going to be 26. So we're having it to be 20. Now can you calculate for me how much is your value of these one? Can you calculate for me the value of these one? So 3000 divided by 20, 107, which is around 110. Okay, so 110. Okay, 110. Your effective depth is now 110. Now, do we calculate d small? Do we need here for this equation? Do we need d small or d capital? D capital. And how would you calculate? Okay. So now if you see here, okay, this is my slab. Now this is my slab, where this is d capital, and the distance from the top till the center of the bottom bar is representing my d. Now if it's one-way slab, only we have one d. Okay, we have one d. If it's a two-way slab, then we have two d's. We have one d till half of the diameter of y, and we have another one till half of the diameter of x. Okay, now since our problem was a one-way slab, and since it's a one-way slab, okay, since it's a one-way slab, if we go and see it once again here, okay, once again, if you see here, we are having lx, this is lx, this is ly. We are designing for lx, so we are seeing from this particular view. So you will be saying what? you will be seeing the white color, one of white color bars, and then you will see the black colors to be circle. If I look from the side of LX, I'll see only one white color bar, which is in this way. So I can see one only because the others are parallel to this line. And then we have the we have the red black dots, okay, which is representing the other side reinforcement. Now, if we take a zoomed section, and this is D capital, this is whatever we refer to dy in case of a two-way. In case of a one-way, there is no dy. In case of a one-way or two-way, in case of a one-way, we call this one to be d. In case of a two-way, we call it as dx. Now, if we take a zoomed section, okay. Now what do we have? We have, this is representing my bar now. I'm just trying to make it a little bit bigger. The distance from the top till half of the bar is whatever we call it as d. From the top to the bottom, this is what we refer as d. Now the remaining between the two is this particular dimension, which is representing the cover and half of the bar. So we need to get first the cover, and then we need to get half of the bar. Are we clear? Are we fine? Okay. Why do we have the cover? Why do we have the cover? The cover is done for what exactly? We are doing the cover mainly to protect our steel, right? We are doing, okay, we are calculating, or we are putting a cover to protect our steel. Now, do you remember the first lecture when we have talked about concrete and steel? First class when we have talked about concrete and steel, we said steel can be affected by two things. Steel can be affected by either water or moisture. We said can be affected by fire as well. Okay. So we said, if you remember, we said steel can be affected either by water or by fire. So the cover is having two categories. There are covers special made for fire, and then there are ones for protecting you from water. Now for us, we need to get the maximum of both. If my member is to be designed for both fire and water, okay, if it's designed for both fire and water, then it should be protected from both of them. Now, did I talk to you about the mild, moderate, severe, very severe? Did I talk to you regarding the different conditions of water? I talked, right? Okay. Now, for fire there is no, the code didn't explain it further. You can use your common sense and your logic. Now, if I design, for example, a hospital, and if I design a house, which one would require more fire resistance? A hospital versus a house. Would you give more fire resistance rating for a place you know how to escape from? You know everything about it, or you will give it to a place where it is somehow new for you and you didn't spend a lot of time understanding it? The hospital, right? Would you give it to a place where, would you give more fire resistance to a place where a lot of people are there or less people are there? Okay, Okay, so you need to use your common sense. You need to use your common sense to judge approximately how much fire resistance is required. When I say, for example, 2 hours of fire resistance, it means that this building will resist a fire of 2 hours before it get collapsed. So you have, let's say, 2 hours to evacuate the building. Are we clear? Are we fine? Okay, very good. Now we need to go and check our cover. Now the question says for us, says for us that we need to design it for a mild environment and a fire resistance of 2 hours. The office, so normally people will be there. Mild environment, it means that it's in a regular zone where we don't have water, we don't have rain, we don't have seawater. Okay, so mild environment and fire resistance. So I'll just go to the code and check. Let me open it from here a bit for you. So the things that I want is the grade of concrete. So the grade of concrete is 30, and then a mild environment. Okay. Use the other problems table, which is durability. Now, in this question, did they mention for you fire? In this question, did they mention for you fire? Do you see any place where fire is mentioned? In this question, which I'm showing you right now. If fire is not mentioned, so you only check for water or moisture. Are we clear? Are we clear? Okay. So normally buildings for sure will be designed for moisture, but not all of them are designed for fire. Although in reality, you need to take both. Are we clear? So if I go here for durability conditions, you will see that I have only taken mild condition. Okay. Now it says mild condition. Now in this problem, it's 35. Okay. In this problem, it's 35. But anyhow, I'll show you how to find the 35 and the 30. So we have this table, which is mild. Now we'll come to this table. Now this table, if you see, it says for you mild, moderate, severe, very severe, most severe, oppressive. So this is clearly the table for the cover of the moisture. Okay. Now if we go and see, it says for you here, if you are using a grade of concrete C30 and your condition is mild, then your value is going to be 25. If you are using like this question, which is mild condition and 35, mild condition and 35, you will see that it's going to be 20. Now can you notice that the values are decreasing? Can you notice that the values are decreasing? 25, 20, 35, 30, 25, 20, 40, 30, 25. Why these are reducing? Now when it comes to design and tables, you need to concentrate at anything and everything. Now if you have a stronger concrete, would you require the same cover or less cover? If I have a grade of concrete which is 50 and a grade of concrete which is 25, do I need the same cover all over? Now, of course, the one which is having higher strength of concrete requires lesser cover, right? Are we clear? Can you see now, whenever we are increasing in terms of grade of concrete, you will see that your cover is reducing. So now for the previous question, we have C30 and mild, so the cover is going to be 25. So we return back to our question. Where the cover, so D capital is equal to cover plus half of the diameter. Okay. So D capital is equal to 110. That is your D small. So D small we have found it to be 110 plus the cover. The cover we have found it to be 25, but we checked only for moisture. We need to go and check for fire. Yeah, I said we're going to check for fire. Okay. We go for the table of contents. We can check the cover. So where is the cover? So we can check durability requirements. There is exposure for water and there is for fire. So I'll go for durability requirements. Now I can see first the definition of mild moderate. First is going to be the definition of mild moderate severe, and then the table that we have seen earlier. And then we come to the fire resistance cover. Now for the fire resistance, how many hours they have said? They have mentioned for us that we are having 2 hours. So 2 hours. So 2 hours. We'll go for beams. No, we are not designing a beam. Are we designing a floor? Yes, we are designing a floor. Slab is a floor. Is it a simply supported or is it a continuous one? Now you can see that it's a simple support. So for a simple support, the proper cover is going to be 35. So I require 25 to protect me from the regular weather, but I require 35 to protect me from 2 hours of fire. So which one to be picked? 35 or 25? 35 or 25? Of course, you'll be picking the largest of the two. So 35 plus the diameter. The diameter of slabs normally start from 8, but it's very rare. We recommend starting from 10. 10 divided by 2. Now, if you go and calculate, the total depth is going to be 150 mm. So 110 is the effective depth. 35 is cover or fire. 10 is the diameter. So 10 divided by 2, because we said effective depth is till the center of the bar. So we require only the other half. Okay. If we return back, now we have our D. So 24 multiplied by 0.15. So this is going to give you 3.6 kilonewton per meter square. 150 mm is 0.15 meter. 24 multiplied by 1.5 is 36. Okay, so we have got it to be 36 or 3.6. Now, if we go and calculate, it's going to be 1.4 multiplied by the self weight, that is 3.6 plus whatever we got it as finishes, so 1.18 plus 1.6, that is a factor of safety for the life load, multiplied by the life load, which is 2.5. It's assumed. Since it's not given, it's assumed. And whenever it's assumed, you'll start from the minimum bar. If the minimum bar does not cope with the with the loading, you go for the higher one. The minimum diameter to be used for a slab, okay, is 8 meter. Now, according to the code, if you go to the code, it says for you 6 mm. Now 6 mm is not available in the market, so you need to drop it out. So we have 8. 8 is too less to take the load, so normally in practice we start from 10. Okay, start from 10 for the slab only. For the beam, it says for you that the minimum in the code, the minimum is 12. Okay, Are we fine? Are we fine? Okay. So how much is the value of W? Can you calculate this for me? The value of W. Quickly, because we have spent the whole lecture in a problem that you should know from design one. So 10.69. So 10.69 is your W. Your L square is 3 square because we are designing for the short, divided by 8. So give me the final value. The final value is 12. Okay, so 12.03 kilonewton meter. So this is the answer of this particular problem. I have tried to explain a lot of things from one way to two way, so you'll be knowing even if we start later solving the two way. Okay. You go to the Excel. We go to the Excel. We go to Excel to verify our solution. Okay. Now, if you see, can you see this Excel? Can you see the Excel? It says for you A to F. So we have only one grid. We have only, you can see now how many spans are there? 3. 1, 2, 3. So I'll just say it is from A to B. This will not change your value, but anyhow. So now it's A to B. How many, what is the support condition? Is it simply or continuous? Is it simple or continuous? Continuous is C, simple is S. Simple, if you remember. So now you change. Now see what is happening in this particular, see what's happening in the diagram shown. Now you can see that there is a bending moment happening at the support. If we change the value from continuous to simple, then you can see that the bending moment at the end supports are equal to 0. Okay. Now how many spans do we have? How many spans do we have? We have only one span. We have only one span. What is the maximum span? Did I tell you that there are series of offices near to each other? Told you only one, right? So one span only. Okay. What is the maximum span? The maximum span is 3. Okay, the maximum span is 3. We're designing only for the short. When I say why it's mentioned maximum span here, because it refers to a number of spans. So if I have 3 spans, the first one is 3, the second one is 3.2, third one is 3, then I should be taking the maximum of the 3. Okay, it does not refer, maximum span does not refer to the long direction. So 3, what is your thickness? What's your overall depth? Our overall depth is 150. The cover taken is 335. Additional weight or additional dead, which is 1.18. So now we should be getting according to the, let me make just let me make the density to be 24. Rate of concrete to be 30. Okay, so we should be getting 10.69. You should be getting 10.69 as W. So we have got it to be 10.69. Okay. You will see that this is 0.125. This is the coefficient that we are referring to. From where we have got this coefficient, we say it's W square over 8. So 1 divided by 8 is going to be 0.125. So this is our factor. How much is your moment? Your moment is 12. Are we clear? Now one person will say, now here your D, you have got it to be 110, but here your D is going to be 107. Why is that? The main difference is happening in terms of the diameter used. So here it's 10, here it's 16. If you change this one to be 10, then your depth is going to be 110. Are we clear? Are we fine? So now we have checked our solution with the Excel. This is how I'm going to verify your answers and your quizzes and your tests by using an Excel. Okay, are we fine? Any questions for today's lecture?
Sir, for the diameter of the steel,
Yes.
when we increase the diameter, it was 10. For example, we increase it into 12.
If it fails, right? If 10 is not sufficient to take the moment, then you need to increase it.
According to the condition, if it's simply or continuous.
See, a basic idea of how you choose the diameter is based on the moment. That's a basic thing. Now here we said, now we have first we start with W, or we start with dead load and live load. These dead load and live load will merge, giving me W. This W will merge, giving me M. This M will go and merge, giving me AS. Right? So here 1.4 into dead plus 1.6 into live. Here we are using, for example, M is equal to W square over 8. For example only. Here we are using an equation of AS is equal to M divided by 0.95 FYZ. Okay, it means that if your loading is increasing, your W is increasing, your moment is increasing, your AS is increasing. And if your AS is increasing, AS is having an area of by D square over 4 or by R square. So whenever your loading is increasing, of course your AS is going to increase. If that diameter that they have chosen is not sufficient because of the extra loading, then I need to change my diameter of the bar. Okay. Are we clear? Any question? No questions. If no questions, go to your e-learning and solve that question, which is available for you. We have finished the class that we didn't start. Okay. Hopefully next class we are going to continue our problem, the two-way slab problem. So the extracts are already uploaded for you.